This is the second part of our building load calculations and design principles lessons. Okay, this one we're going to be talking about methods of heat transfer. That's how heat moves through building materials and other substances. There's three methods of heat transfers. We have conduction, we have convection, and we have radiation. Okay, if we look at the diagram on the side, okay, we can see all of those in that picture. We have conduction, we have convection, and we have radiation. Convection is the heat that's blowing out of the stove onto the person and into the cat. Conduction is the heat that's heating the heat kettle, and radiation is the heat that's heating the wall behind the stove. But we're going to talk more about each one of these. Conduction is the first one I want to talk about. Conduction is heat transferring through solid materials. For example, the flame is heating the pan. The pan is conducting that heat to the water inside of it. Okay, from experience, we know if we touch the sides of a pan with boiling water, you'll be burned. Why? Okay, the heat's coming through the side because of conduction. Now, the handle is made of material that doesn't conduct heat as well as the material of the boiling pot. So heat conducts through different materials at different rates. That's something very important to remember. Conduction transfers heat through matter from particle to particle. Okay? Again, through matter. The thermal conductivity, or K, is how well the material transfers heat. The higher the conductivity, the faster heat transfers. Conduction is inversely proportional to the thickness of the material. Double the thickness of the material while maintaining the temperature difference between its size, the rate of the heat transfer is cut in half. Okay, so increase the thickness, the heat transfer gets less. In buildings, conduction occurs easily through building materials such as metal, glass, and concrete. Poor conducting materials are usually used as insulating materials. Fiberglass, insulating foams, mineral wool, all of these are poor conducting materials, and they're used for insulation. The ability of a material to conduct heat is measured by a property called thermal conductivity, or K. Dividing this value by the thickness of the material, which is referenced as L in the formulas, measured in inches, yields another very important term called the coefficient of heat loss, or the U factor. If you remember anything about this small portion of design, remember what a U factor is. It's the thermal conductivity divided by the thickness of the material. It's called a U factor, and that's the coefficient of heat transfer. This becomes very important when we start talking about design. Conduction, we have a normal sequence to solving conduction problems. We want to look up the R value for the materials in a building cross-section, add those values, and then take the reciprocal of that answer to get the U factor. Now, what is a reciprocal? Okay, so let's see if we can draw a pen on here. Okay, so if I have an R value, and I'm doing this with a mouse pointer, so sorry about that. If I have an R value of 100, okay, if I want to get my U value, or my U factor, we take the reciprocal, which is 1 over 100. Okay, and if you pull out if you do the same thing, and I'm going to give you a chance to do it here, if you pull out your handy dandy calculator, 1 over 100 is 0.01. Now this one is easy because it's dealing with 1 and 100ths. Okay, but we can have different values. Okay, if I have an R value of, let's just say 90, my U value would be 1 over 90. And again, sorry about the writing, but I'm dealing with basically a mouse pointer. So if we take 1 divided by 90, my R value here, or my U factor, is 0.011, and basically forever. Okay, so my R factor and my U factor are just reciprocals of each other. Reciprocal means take that number and divide it into 1. So 1 over whatever the number is. Conduction can happen in fluids as well as solids. Metals tend to feel cold, but they might not be cold. They only feel colder because they conduct heat away from your hand to an object colder than your hand. Again, a feeling of cold is just loss of heat. The next one method of heat transfer I want to look at is convection. ASHRAE defines thermal convection as transfer of heat by the movement of fluid. Okay, for heat to be considered convection, fluid in contact with the surface must be in motion. If not, the mode of heat transfer is conduction. Now we extend that a little bit. Okay, we can extend convection to transfer of heat by the movement of air. Okay, but it's a movement of another material. So convection heat transfer occurs when fluid at different temperatures move around within a space. And this is an example of an old-fashioned lava lamp. Okay, the fluids are moving around in a space. That's convection. So look back at our pot of boiling water. What's the example of convection in this graphic? Although the heat transfer through the metal of the pot itself is conduction, because the molecules of the pot are in direct contact with one another, the movement in the boiling water is an example of convection. Another example of convection is called forced convection. A fan cools a computer circuit board. Natural convection is cool air coming into a warm room. So again, we have a couple different examples of convection. Forced convection, I'm moving the material. I'm forcing the material to be moved. Natural convection happens on its own. Cold air sinks, hot air rises. Convection is the transfer of heat energy in a gas or liquid by movements of the currents. The heat moves with the flow of the fluid. Convection is also responsible for making the macaroni rise and fall in a pot of heating water. Warm portions of the water are less dense and therefore rise. The cooler portions of the water fall because they're more dense. Convection heat transfer occurs when fluid at different temperatures move around within a space. Again, the hot water is less dense, it rises. Cold water is more dense, it falls. We have two types of convection. We have free, which is called natural convection, and we have forced, which is called mechanical convection. Free convection uses the natural buoyancy of the fluid to drive the convective flow. Wintertime, cold, that's heavy air falls down windows creating drafts. Hot, light air rises from counters it. Okay, so we have air patterns within a room that's naturally occurring. Okay, the hot air rises in the center of the room, goes to the outside wall, starts cooling, and drops down the outside walls, so you have a natural air current that can occur in a room. Again, heat is always going to try to flow from hotter areas to cooler areas. Forced or mechanical convection uses a fan or pump to force the flow of heated fluid. For example, a ceiling fan is an example of forced convection. The natural thermal stratification, hot air rises, is counteracted by the fan pushing the warmer air back down to the living zone. Especially in a house or building with vaulted ceilings, you don't want all that hot air up along the ceiling level. You want to force that back down into the room. Similarly, with air conditioning, you don't want all the cold air just to be just around your ankles. You want this mixed up in the room. Warmer rising thermals due to heat rising from the earth is an example of convection. As the warm air rises, cool air comes in from the sides to take its place. This is a setup. This setup is circulating flow of air. Convective heat transfer occurs when fluids at different temperatures move around within the space. Okay. Convection uses the natural buoyancy of the fluid or gas to drive the convective flow of air. Okay, again. Forced convection depends on a pump or fan to force the flow of heated fluid or gas. Natural convection uses only the natural buoyancy of the fluid to drive the convective flow. Hot air rises. In the winter time, again, the cold air cascades down windows, creating unpleasant drafts. In a good design, these drafts are countered by rising currents of heated air from a register or radiator located below the window. Forced convection depends on a pump or fan to force the flow of heated fluid. So convection, again, it's movement of air or fluid to move the heat around a space. We have one more type of heat transfer we have to talk about, and that's radiation. Radiation is electromagnetic energy. Okay? Radiant energy is emitted by all matter whose temperature is greater than absolute zero. That's 0 degree Kelvin. The warmer the radiant object, the shorter the frequency of electromagnetic waves it emits. Types of electromagnetic waves include electric currents, heat, radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays, and cosmic rays. Radiation does not need material to transfer heat from one location to another. This is unlike conduction or convection. We don't have to have anything to help it flow. Radiation goes on its own. It travels outwards from its source in straight lines at the speed of light. Radiation cannot bend around corners, but it can be reflected with mirrors. Radiation, a surface emits thermal radiation to any cooler surface within sight of it. Let's think about that. I'm going to say that again. A surface emits thermal radiation to any cooler surface within sight of it. Basically what this means, within a straight line of it. An example of this is a person sitting in front of a campfire on a cold night. Okay? Radiation is coming out of the fire and warming the person sitting in front of the campfire. The air between point A and point B might not be warm, but the person is. What about a toaster? A toaster element is not in direct contact with the bread, but that red hot toaster elements toast that slice of bread. Okay, so a question here. Of the three methods of heat transfer, how does solar energy get to the Earth? Is it radiation? We know there's a vacuum between the sun and the Earth. We know it doesn't require a solid, gas, or fluid transfer to radiation. So radiation is the only heat energy that can travel through a vacuum. And again, this is very important as we start talking about building design. Radiation is the only heat energy that can transfer through a vacuum. And I want you to start thinking about windows. Let's go through a couple exercises on these different methods of heat transfer. So what method of heat transfer is this one? Is it convection? Is it conduction? Or is it radiation? Okay. So depending on what object we're looking at, convection is from the radiator to the air around the radiator. Conduction is from the radiator to the cap. They're in direct contact. Radiation is from the radiator to any line of sight cooler object. In this case, I'd be guessing the wall behind the radiator. Okay, what about this method? What methods of heat transfers are in this picture? Conduction, between the cup and the spoon. Convection, the liquid to the air temperature. Radiation, probably some very little. How about this one? Let's just say the ball is a little warm. Conduction, the ball to the ground. The ground will probably have a cooler temperature. Convection, if it's a warm day, the air to the ball. Radiation, the sunlight to the ball. Keeps that ball warm. How about this one? Where do I have convection? Where do I have conduction? And where do I have radiation? Conduction, the wood to the ground. Convection, the fire to the air, the natural air currents. Radiation, the fire to the surrounding rocks and legs. How about this one? Conduction is the grate to the bottom of the pot to the water. Convection would be the boiling water and the air above the boiling water. Radiation, the grate to the metal holder, the pot to the metal holder, and the pot to the stovetop. Okay, a few other questions for you. Okay, if you happen to have this book, which is available through ESCO Institute, okay, some workbook exercises. So brownies bake in a glass pan using which two methods? The answer is convection and radiation. Heat in the room moves with warm currents from warmer areas to cooler areas. Is this convection, conduction, or radiation? Correct answer is convection. You feel the heat of a wood stove when you stand next to it. What method of heat transfer is this? It's radiation and convection. The heat is coming through the space to you, and the warm air is moving around. Warm water rises in a lake. Cold water descends. Is this conduction, convection, or radiation? Patterns. Hot water rises, cold water descends. It's convection. A thermometer under your tongue shows that you have a high fever. Is this conduction, convection, or radiation? It's conduction. Solid object to solid object. The sun transfers its heat to our planet through space. Is this conduction, convection, or radiation? Radiation. We've talked about it. Radiation is the only way for heat to travel through a vacuum. On a cloudless night, heat escapes from our planet and goes into space. Is this conduction, convection, or radiation? Once again, radiation is the only way for heat to transfer through the vacuum of space. You place a spoon in a cup of cocoa and it gets hot over time. Is this conduction, convection, or radiation? It's conduction. Okay, solid object, molecule to molecule. Blank is measured with a thermometer. Is it heat, temperature, or radiation? B. Temperature is measured with a thermometer. Heat might include temperature, but the heat goes way beyond temperature. The final one. A thermos bottle has a shiny interior. What type of heat transfer does it prevent? Is it conduction, convection, or radiation? It's radiation. Because we want to bounce those rays off, okay? It's using a mirrored surface, basically. So again, we've talked pretty in depth about the three types of heat transfer methods, okay? We have conduction, we have convection, we have radiation. Radiation is by rays, it's line of sight, it's the only method that can travel through a vacuum. Conduction is object to object, okay? It's molecule to molecule heat transfer. Convection, air or fluid, can be both natural and mechanical, or natural and forced, depending on how you want to look at it.